So this is ELC131, Circuit Analysis 1, and this presentation is an introduction to filters. Now, a filter is simply a circuit that's designed to pass selected frequencies to a load and block other frequencies from passing to the load. So we look at a block diagram of a simple filter circuit in figure 1, and of course we've got some input voltage and then a filter and an output voltage that's passed to the load resistor. And our filters fall under one of four categories. They're either low pass filters, high pass filters, band pass filters, or band stop filters. And some texts refer to these as band reject filters. And in the following slide, we'll look at the frequency response curves of these filters. And frequency response is just the way, the terminology we use when we graph the output, which can either be power or voltage or current, as a function of frequency. So we see in figure 2 the frequency response of a low pass filter. And note, if you will, of course, at low frequencies the load power is great, and at high frequencies the load power is very small. And in figure 3 we see the frequency response curve of a high pass filter. And again, at high frequencies, the load power is great, and at low frequencies, the load power is very small. Figure 4 shows us the frequency response curves for a band pass filter. And notice that at some frequency, we pass, the load power is great, and at frequencies below and above that frequency, the load power is small. And lastly, in figure 5, we see the frequency response curve of a band stop filter. And at some selected frequency, the load power is minimal, and at frequencies below and above that frequency, the load power is great. So let's start by discussing an application of filters. And I always like to use this, this application of a simple audio amplifier and a three-way speaker system. So our audio amplifier produces AC signals ranging from 20 Hertz to 20 kHz. And it sends these AC signals to a speaker or to a set of speakers. So in figure 6, we see the audio amplifier, and we see three speakers: the tweeter, the mid-range, and the woofer. And the reason we do this is that it's difficult for one single speaker to reproduce audio signals that range all the way from 20 Hertz to 20 kHz. So in order to provide improved sound quality, or what's called fidelity, we use what's called a three-way speaker system, where the woofer is used to reproduce audio signals ranging from 20 Hertz to 2 kHz, the mid-range speaker to reproduce audio signals from 500 Hertz to 4 kHz, and the tweeter reproduces audio signals from 2 kHz to 20 kHz. Now, the reason we do this is that for these low frequency audio signals ranging from 20 Hertz to 2 kHz, we're asking the speaker to move in and out fairly slowly. And of course, with the tweeter, we're asking this speaker, the coil in the speaker, to move in and out at up to 20,000 times a second. And appreciate the fact that in order to receive a lot of volume at low frequencies, we need a speaker that, in some cases, the woofer is 15 inches in diameter, and can weigh up to 12 pounds. And it's impossible to get a 12-pound coil to move in and out 20,000 times a second. So this is the reason behind using a three-way speaker system. And what our filters do is they limit the frequencies that can pass through to the woofer by using a low-pass filter in series with the woofer. And of course, we limit the frequencies from 500 hertz to 4K hertz passing to the mid-range using a band-pass filter, and of course use a high-pass filter in series with the tweeter, so only the high-frequency audio or AC energy can go to the tweeter. Now, when we quantify different speakers, our key metric is the cutoff frequency. And the cutoff frequency is simply the frequency where the AC signal is considered to be filtered out. And the decision was made that the cutoff frequency would be the frequency where the output power was 1/2 of the maximum output power. And this cutoff frequency is also referred to as, of course, the half power point. Now, if we look at the equation that expresses the relationship of power in a system in decibels, it's that dB equals 10 times the log of P out over P out max. And 10 times the log of 1/2 equals negative 3.01 decibels. So the cutoff frequency is also referred to as the negative 3 dB point. Now, when we look at a circuit with respect to voltage, the cutoff frequency is the point where the output voltage drops to 70.7% of the maximum. And this, of course, is because P equals V squared divided by R. So when we take the square root of P divided by 2, we get 0.707. Now, the equation that lets us express voltage ratios in decibels is that the dB equals 20 times the log of V out over V out max. So if we take 20 times the log of 0.707, we get negative 3.01 decibels. So again, regardless of whether we discussed filter input and output in terms of power or voltage, the cutoff frequency is still the negative 3 dB point. Now we look at the frequency response of a low-pass filter. And we see a simple low-pass filter in figure 7. We have an input voltage of 1 volt. The filter is stated to have a cutoff frequency of 2 kHz. And of course the output is passed to some load. Now when we use this term frequency response, it's simply a graph with frequency on the x-axis and either load power or load voltage or load current on the y-axis. So in figure 8, we see the frequency response curve of this low-pass filter with the output described as power. And note, if you will, that at the cutoff frequency, 2 kHz, the output power has dropped to 50% or 1/2 of the maximum output power. And in figure 9, we see the frequency response curve of this same filter with the output measured in volts rather than watts. And again, the cutoff frequency, 2 kHz, is the point where the output drops to 70.7% of the maximum, or 1 volt. Now these two plots or graphs are shown with a linear x-axis. And what this means is that the distance from here to here, 2 kHz, is the same distance as from here to here, which is another 2 kHz, which is the same as the distance from here to here, which is another 2 kHz. So the x-axis is what we call a linear scale, meaning the spaces are the same for any given value of frequency. And of course, the y-axis value is on a linear plot also. Now, the difficulty with using these two graphs with a linear x and a linear y-axis is the fact that this graph is so extremely non-linear through this region, it makes it very hard to see kind of what's going on down here near the cutoff frequency. So to make it a little easier to see what's happening graphically, we can plot the x-axis on a logarithmic scale. Now what that means is that the distance on the x-axis from 10 Hertz to 100 Hertz is the same distance as from 100 to 1000. In other words, the scale increases in decades. So the distance, again, from 10 to 100 is the same distance on the x-axis as from 100 to 1000, which is the same as the distance from 1000 to 10,000. And notice what this graph has done for us. It's expanded the graph at the lower frequencies, and it's compressed the graph at the higher frequencies, which makes it a lot easier for us to really see what's going on closer to the cutoff frequency. Now this graph still has the problem in that it's still very nonlinear as frequency gets higher and higher and higher. And this makes it difficult for us to be able to predict the output voltage at a particular frequency. So what we do is create what's called a Bode plot. And the Bode plot is simply a graph that plots the x-axis on a linear scale, a logarithmic scale. Again, the distance from 10 to 100 is the same as the distance from 100 to 1000. But the y-axis is plotted in decibels. And note that when we look at this frequency response curve, how linear this graph appears at frequencies above the cutoff frequency. And this makes it much easier for us to be able to predict the output voltage at a selected frequency because of the linearity of this curve. Now, when we look at what are called single pole filters, and these are filters that have one RC or one LR pair, these filters are stated to have a roll-off of -6 dB per octave and -20 dB per decade. And when we talk about roll-off, we're simply talking about the slope of this graph beyond the cutoff frequency. So the slope of this curve beyond FC is what's called the roll-off. Now, recall from our earlier discussions on alternating current that an octave is a change in frequency of either ×2 or divided by 2. And a decade is a change in frequency of either ×10 or divided by 10. So looking at the plot or the Bode plot shown in figure 12, note that at 2 times the cutoff frequency, this point right here, my output has decayed or declined by 6 decibels. Now again, at the cutoff frequency, the signal had already dropped to -3 decibels, and from FC to FC times 2, the signal drops by an additional 6 decibels, which puts it at -9 decibels. And of course, at the cutoff frequency times 4, the output has dropped to -15 decibels. Again, another -6 dB drop. And at the cutoff frequency times 10, the output has dropped to -23 dB. Again, from FC to FC times 10 is 1 decade. So one of the benefits of using a Bode plot is that we can fairly easily predict the output voltage at these integral multiples of the cutoff frequency. Excuse me. Now we look at the frequency response of a high pass filter, and in figure 14 we see the output power of the filter as a function of frequency, and in figure 15 we see the output voltage plotted as a function of frequency. And again, our filter has an input voltage of 1 volt and a cutoff frequency of 2 kilohertz. And these two plots, figure 14 and 15, again, are plotted with a linear x-axis. Again, the distance between 0 hertz and 2000 hertz is the same as the distance from 2000 to 4000. And as we saw with the low pass filter, it is difficult to see what's going on down in these lower frequency regions around the cutoff frequency with these graphs. So just like with the low pass filter, if we plot this frequency response with the x-axis on a logarithmic scale, again, the distance from 10 to 100 is the same space as the distance from 100 to 1000. This is what's called a logarithmic scale. And notice when we plot this frequency response on with a logarithmic x-axis, that again it expands these low frequencies and compresses the high frequencies, and it makes it much easier to see what's going on in and around the cutoff frequency. However, most often we will again plot this frequency response using a Bode plot. And the Bode plot has the x-axis with a logarithmic scale. Again, the space from 10 to 100 is the same as the space or distance from 100 to 1000, but the x-axis, the y-axis is plotted in decibels. And again, note with this Bode plot, the linearity of the curve at frequencies below the cutoff frequency. So the reason we use the Bode plot, again, with the x-axis, it expands the low frequency values and compresses the high frequency values, and plotting the y-axis in decibels gives us a very linear graphical response of the filter. Now, bandpass filters, as we'll notice looking at the graph in figure 19, they have 2 cutoff frequencies. There's 2 points where the output voltage drops to 70.7% of the maximum. Now the filter we're looking at, shown in figure 18, has an input of 1 volt and it has a center frequency of 2 kilohertz. Now because there's 2 cutoff frequencies and we refer to them as F1 and F2, I have seen some texts refer to these as FC1 and FC2, and I've even seen texts refer to these as FL and FU for F lower and F upper. But when discussing these bandpass filters, we use the term bandwidth to describe the range of frequencies between F1 and F2. Now, generally speaking, we can approximate the center frequency, F sub O, by finding F1 plus the bandwidth divided by 2 and F2, which equals F2 minus the bandwidth divided by 2. However, looking at the frequency response curve in figure 19, notice that this graph is somewhat non-symmetrical, meaning the distance between F1 and F2 is not exactly the same as the distance from, the distance from F1 to F0, F naught, is not the same as the distance from the center frequency to F2. So this graph is really not symmetrical. However, for most purposes, we can use this equation for a valid approximation of the center frequency, F sub O. Now, the true value of F sub O is what's called the geometric average of F1 and F2, which is calculated as shown, the square root of F1 times F2. Now, an additional quantifying factor for bandpass filters is what's called the quality factor, symbolized with the letter Q. And for bandpass filters, the quality factor Q mathematically is F sub O divided by bandwidth. The quality factor is simply a numeric value that expresses the selectivity of the filter. In other words, the smaller the bandwidth, the greater the Q factor. Now, with this frequency response curve shown in figure 19, again, it's hard to see what's going on around F1 and F2 because this graph is so extremely nonlinear in this region above the center frequency. So when we plot the frequency response of these bandpass filters, we can improve the graphical response by plotting the x-axis on a logarithmic scale. Again, note the x-axis is on a logarithmic scale and the y-axis is on a linear scale. And notice what this has done with our graph is that it's again expanded the lower frequencies and compressed the upper frequencies, but it makes this curve much more symmetrical in appearance. However, it's still difficult to predict the output voltage at a selected frequency because of the extreme nonlinearity of the curve below and above the cutoff frequencies. So just like we did with low pass and high pass filters, we typically use a Bode plot to graphically illustrate the response of these filters. And again, our Bode plot uses a logarithmic x-axis and the y-axis is expressed in decibels. And note, with the frequency response of this bandpass filter as a Bode plot, notice how extremely linear the filter response is below the cutoff frequency and above the cutoff frequencies. This makes it much easier to predict the output voltage at a selected frequency because of the extreme linearity of these graphs. Now, the fourth classification of filters is a band stop filter. Again, these are sometimes referred to as band reject filters. So in figure 22, we see a simple band pass filter with a center frequency of 2 kilohertz and an input of 1 volt. And just like the band pass filter, the band stop filter has 2 cutoff frequencies, F1 and F2. The distance or the range of frequencies between the cutoff frequencies is called the bandwidth. And again, for most applications, we can approximate the center frequency by taking the lower cutoff frequency, F1, and adding the bandwidth divided by 2, or the upper cutoff frequency, F2, minus the bandwidth divided by 2. However, again, this just provides us an approximation, because you'll notice, looking at this frequency response curve, the distance from F1 to F0 is not the same distance as from F0 to F2. Again, this filter is slightly non-symmetrical around the center frequency, just like the band pass filter was. So in order to calculate the true center frequency, we have to find the geometric average of F1 and F2. And just like with the band pass filter, we use the quality factor Q to quantify the selectivity of this filter. And mathematically, it's the same as the band pass filter. Q equals F sub O divided by bandwidth. Again, the Q factor gives us a numeric value for the selectivity of the band stop filter. Now, we look at the frequency response curve in figure 23, and again, this is plotted with output voltage as a function of frequency, with frequency on a linear axis. And again, it's difficult to see what's going on at the lower frequencies. So we'll plot this with a logarithmic x-axis, as we did with the low pass, high pass, and band pass filters. So figure 24 shows us the same frequency response curve, or the frequency response curve for that band stop filter, with the x-axis as a logarithmic, or on a logarithmic scale. And again, with a logarithmic scale, what we do is we expand the lower frequencies and we compress the upper frequencies. And notice again, looking at the graphical representation of the response curve, our graph looks a lot more symmetrical now than it did in the previous plot, where the x-axis was linear. But just like with the low pass filter, the high pass filter, and the band pass filter, typically we will plot the frequency response of this filter using a Bode plot, where the x-axis is logarithmic and the y-axis is in decibels. And notice what this has done is it's made our frequency response much more linear in this region, closer to the center frequency. So again, with the Bode plot, it makes it much easier to predict the response of this filter at a selected frequency. So with this presentation, of course, we looked at an application of filters. We have, of course, classified filters as either low pass, high pass, band pass, or band stop filters. And we've looked at the frequency response curves of these 4 filters, with the frequency response curve shown as power or voltage and the x-axis plotted with a linear scale. We've changed the x-axis to a logarithmic scale, which expands the low frequencies and compresses the high frequencies, providing in some cases a much more symmetrical graphical representation of the frequencies of the filter's operation. And then finally we looked at the use, or the showing the frequency response using a Bode plot. And again, the Bode plot plots the x-axis with a logarithmic scale, and the y-axis is plotted in decibels.